please remember if I forget to record. I'm going to go back and forth. You want to come to class so you can see some videos and we can talk about them. All right. I might send out some emails as well with some links. All right. So let's go over it. Now, here's the deal. I have access to Canvas, but I don't base myself on Canvas because I have my website that I've had up for at least 15 years. All right. So here's my website, kkuniyuk.com. All right. And I sent you the URL. All right. Go down here, class websites, Math 141. You can go directly to my, or you can go directly to my Math 141 site. All right. And you see the YouTube link. The YouTube link will take you to the videos, or I'll show you where you can watch the lecture videos, and I'll try to upload videos of the class sessions as well. All right. So clicking here. All right. And remember, you want to go to playlists, so then you can get, and then go to the week. All right. And then you can get to the various lists of videos. All right. Canvas, you know, that's good for discussion boards, for students to communicate with each other and access to NetTutor, but I don't use Canvas too much. All right. Okay. Again, feel free to chat if you have any questions. Chat here anytime you have any questions, or unmute yourself. We tend to chat. Okay, now in the syllabus, I promised the Alex extra credit opportunity, and I'm going to email more on that either tomorrow or Thursday. Okay, I've been pulling all-nighters, so I'll try to get that out to you within the next 48 hours. Okay, but it's great. It's a great opportunity. The syllabus is here. I'll go over that. Here are your homework assignments. So your chapter 0 homework is right here. Homework assignments. Here's your chapter 0 homework. All right, and you're going to turn in the homework solutions on your own paper. Scan them in, email them to me. The answers are here, right? But you have to show me the appropriate work. Some of these are answer only, but you know, some of these do require some work. Some instructions, all right? They're also on here. You do not have to do any problems indicated as additional problems. All right? Write your name and Math 141 in the upper right-hand corner of your sheet or a cover sheet. In the homework, you might see these things which indicate parts of my notes, like part A of my notes. If you're struggling on time, at least do a few problems from each section. Okay, don't skip entire sections. Clearly separate sections. Okay, do we have to print it out, or can we write it out on a tablet and send it that way? We don't have to print anything out. Just email me. Okay, email me, scans, photos. Okay, so you don't even have to write on paper if you're good at typing or whatever, a tablet, that's fine. Do you do homework on a separate sheet of paper? Most of you will. That's probably easier. And then you scan or email. But if you're good at typing or tablets, that's cool. But you're going to send it to me electronically. Don't come to my place. The additional problems are for extra practice and just for a challenge, but they're optional. They're not required. Although I'm happy to talk with you about them if you wish. All right. Clearly separate sections. The sections are key to my online notes, not a textbook. No textbook required. Basically, I'm referring to my online notes. They're free. And they're almost all typed. The ones for chapters 0 and 1 are book-like, nice and well typed, but kind of long. Chapters 2 through 9, more like board work. Chapter 10 is mostly handwritten. Should work where appropriate, because I'm going to grade your work. Okay. Use good form and procedure. Don't be late. You don't have to rewrite the questions. I give you the questions. If it helps you, that's fine. Feel free to mark up your homework, but don't make it so much of a mess I can't tell you've done it. Feel free to ask me about the homework. All right. And email me any suggestions. Notice I'm not saying anything about exams. I'll be honest. At this time, I do not believe in online exams. Go ahead and say yay. I don't believe in online exams.
Yay.
I would rather have you folks work on my excellent, well-organized, well-thought-out homework assignments. We'll work on them together. If you put in a good effort and you know your stuff, then you should do fine. All right? That's fine with me. So work on my homework assignments. I designed them very carefully. Okay? I edited them very carefully. All right. But you're going to learn a lot. Okay, so it's not a matter of me being easy. You're going to learn a lot from my homework assignments. I don't throw you random questions. They're well-organized homework assignments. All right, so you're going to learn. All right? Okay. Oh, don't think it's going to be an easy class. All right. Okay. Class notes. So again, my notes are here. Okay. They're organized by exam, but you know. Okay. So like chapter 0's here, chapter 1's over here. Okay. In big file or smaller files for like iPhones. So my notes are here. Okay. Old exams and solutions for your benefit. Okay. I managed a couple of exams in the spring. That's fine. And some extra resources. All right. So that's my website. Any questions about my website before I go to my syllabus? Any questions? All right. Let's go to my syllabus. Now, I assume that you can read my syllabus. All right. And much like South Park, the human centipede episode, your continued presence in this class implies that you are accepting my terms and conditions. All right. Or South Park 2 dated for you folks. All right. So I'm going to go over this really quickly, and I want to be done by about 7:35. All right. Okay. I am recording, by the way. I got to check sometimes. I am recording. All right. Okay. So it's Math 141. All right. Pre-calculus. We're going to meet by Zoom at these times. All right. Days and times. Tuesday, Thursday evenings. Sorry, not AM, it's PM. I'm a Nighthawk. Okay, here's my instructor information. I'm not Bobby Lee. I'm Ken Kuniyuki. All right, just call me Ken. That's fine. You don't have to butcher my name. Okay, here are my email addresses. There's no I before the at. Okay, I tend to check my Yahoo account because it has unlimited storage. But if you have like official business, like a recommendation letter or something, then go to my SDCCD account. That's safer for official business. I check my email frequently, but I tend to be very busy in the middle of the week. I am the assistant chair of the math department, so I can get busy. All right. If you ask about homework, please don't give me a list of numbers, okay? Tell me what you're thinking. I want to work with you. Photos can help. My office hours are basically early evening, so basically an hour and a half before my classes, all right? And the idea is that if you email me, we can try to set up a Zoom room meeting in office hours. I will check my email in here in these hours and also throughout. And I sent you the email to my Zoom room. Will all Zoom sessions be recorded? Most of them. We'll see. Part of it might be student preference. Okay, so my website, my general site, my 141 site I showed you. I'm assuming you have ready access to internet and email. All right, you're going to submit homework to my Yahoo account or Canvas. But I mean, I'll, you know, if you submit stuff on Canvas, I guess I can get it. But Yahoo's easier. Okay, on my website, you'll find all the homework assignments and answers. But the solutions we'll go over in class, some of them. All right. Okay. So lots of stuff on my website, and I can help you form study groups. No required textbook. Homework and answers are online. Now, as for the worked out solutions may be given in some class sessions. Now, especially in these sessions or parts of class sessions where we're going over homework problems, part of it might be recorded, but basically I'll say, okay, I'm going to record part of this. And then if students say, you know what, we don't want to record anymore, we just want to do things privately, I may turn off the recording. So if a lot of you are shy, then I may turn off the recording kind of early, and I may just do solutions fairly privately with students. So in terms of the public versus private on working out homework solutions, that depends on the students, okay? I can't guarantee that'll be recorded. However, I'm going to try to record the in-class sessions, and my YouTube videos, they're pre-recorded. Okay. In theory, you could take this class asynchronously in a way, but it helps a lot to communicate with me. You can ask me questions in chat or talk with me between or after class, between or after the lectures and after them. It's good to have me live as opposed to dead. All right. I will tell you what you can skip in class, okay? So yeah, come to the lectures because, and these may not be in the pre-recorded videos. So in class, I can tell you what stuff to skip. Okay. So basically, I'm assuming that you're attending my video Zoom lectures and I have the right to call you on that, all right? In terms of things you can skip, I'm not going to add stuff on, but I could give you some solutions I'm going to end up grading, for example. That's fair game, all right? So I might give help to people who come to my class. But if you do it asynchronously, you won't miss anything if you do what I tell you to do. All right. If you can figure out the solutions. I used to use Larson's text. My notes are based on them, and you can get old editions here, but like for $6, you don't need a new edition. I don't require a textbook. If you want a book, get one for $6, old edition, that's fine. Pre-calc has not changed that much. All right. Okay, the Shams outline for pre-calculus, that's nice. Cheap paperback with problems. All right. Accommodations in DSPS, basically students with disabilities, people in professional or college activities where you'll have trouble coming to class. Basically, let me know ASAP, and we can try to make accommodations as appropriate, like with due dates or whatever. Okay, any questions so far? Feel free to chat or unmute if I'm not noticing. Any questions so far? Any questions so far? I emailed this out to you. I'm just skimming over it as we wait for people. All right, additional help. On the Canvas site, there is a discussion board up, and I do encourage students to communicate with each other, all right? The NetTutor link, free 24/7 online tutoring. That's a great link on Canvas, all right? But I don't use the Canvas site so much itself. There are neat websites on my website. Using each other, well, don't use each other, but collaborate with each other. The Canvas board can help. Tutoring. Okay, so I give you websites for tutoring. There's NetTutor, all right. Star Trio for eligible students. And here, student resources, a nice list of resources for students. Also Mesa Journeys, which I'll show you. Basically, if you need student help. Student services. How do we set up times with you to meet? Email. Okay, or talk with me after class. All right. Deadlines, these are typical for the 16-week term. Now, if you don't want anything appearing on your transcript, then you want to drop by Friday, August 28th. That's Friday of next week. After that, something will appear in your transcript. Before this date, it'll be a W, all right? After this date, Friday, October 23rd, it'll be a grade. All right. Okay. All right. Grades, assignments. All right. Your course score will be out of 1,000 points. A point is a point. So a homework point equals a class participation point. A point's a point. 1,000 points is 100%. All right. And the Alex is extra credit. The homework will be 85% of your grade. Okay, so you're going to have homework assignments corresponding to what would have been exams in the class. All right, so the first and they're worth different numbers of points. So the first homework for chapter 0, which is the hardest chapter, by the way, that's 90 points. All right, people often failed that exam. It's a review. It's a review chapter, and also a chapter where we take basic skills and extend them. But chapter 0 has a lot of stuff. All right. So that's 90 points, and then there are different point totals. There's a big homework that would have been for the final, chapter 7 to 10. That's big, 250 points. All right. You can get the homework on my website. The homework will be graded as a combination of overall completeness and a selection of, and also I'm going to grade selected problems and exercises. So I'll take some problems in the homework and grade them. So there's a little bit of statistics here, right? A little bit of luck maybe, but you want to come to class, get good solutions for all the problems because you don't know which ones I'll pick. Hey, if you come to class, I might give you a hint, right? Like during the sessions. So people who come to my class sessions, they may be rewarded. Although I won't give you new problems in the sessions. All right, no tricks like that. All right, now I expect to discuss some solutions, not all, we won't have time. I expect to discuss some solutions with students in our homework sessions. Again, part or all of which may or may not be recorded. It depends on how students feel. So I might start by trying to record, but then if students say, no, we want to keep it private, I may shut it down. All right, so come to class if you'd like your questions answered. Well, if you want your questions answered, well, yeah, I mean, you can't just speak to a YouTube video, right? Okay, see me. Now, these sessions will be very difficult to understand if you have not studied the material or basically completed the homework. So know your stuff. These homework sessions won't be much help to you if you don't know your stuff, okay? It's to your benefit to be prepared, all right? Think of me as Socrates, and you want to be prepared, and so Socrates can speak with you. I'm not that smart, but pretend I'm Socrates. It is expected that students will be knowledgeable enough to keep up with the homework sessions. All right. Although you are strongly encouraged to do problems as soon as you can, don't procrastinate, homework will typically be due midnight at the end of the day following the corresponding homework session. So for example, if we have a big homework session on Wednesday, the homework will be due midnight, the end of, I'm sorry, your Tuesday, Thursday class. If we have a homework session on Thursday, then the corresponding homework will be due midnight, the end of Friday. So I'll give you a bit more than 24 hours to get things tidy and email them to me. You don't know if there'll be a technical glitch. Before, in the spring, I had stuff due the midnight of the homework session. That was tough. So I'll extend it at least 24 hours. Okay. I expect students to write out or type their solutions to problems on paper or type them on work on a tablet. That's fine. And you're going to email it to me. Okay. So you're going to give me electronic copies of your homework to my email address, preferably the Yahoo one with unlimited storage capacity. It could be 3-4 gigs, doesn't matter. I have unlimited storage capacity. My official SDCCD account does not. So email it to me at Yahoo. Okay, and you don't have to copy the problems. If it helps, that's fine. Expect late homework to be penalized. The last homework, like the final homework, must be turned in on time. Don't make people wait for their grades. Please turn in your homework in the correct order. So section 0.1, 1, 2, 3, 4. If 5's hard, leave some space, go to 6, and then you can go back to 5 later. But please don't turn in your homework like a football game, right? 1, 7, 3, 9, because then I won't know if you've completed it, right? So don't confuse me. If you confuse me, then I might take off points, right? So you don't have to work out the problems in order, but present it to me in order, right? Okay, again, clearly separate sections, clearly put your name and Math 141 in your homework. Of course, if you're emailing, I hope you have a clear email name. On your homework, show work where appropriate. Folks, I'm gonna grade a lot of your work, okay? I'll give you answers, they're online already, but I'll grade a lot of your work. And if you had a friend who took me for this class last semester, they may have done the wrong work. Okay, points may be deducted for submissions that are incomplete, illegible, systematically copied, late. They don't adhere to good form and procedure. They're messy, they're unordered. Okay, so points can be deducted for all these things. Do you want them in a PDF? A PDF is ideal, but not necessarily. Class participation, 15%. Okay, various forms of possible participation. Oh, good news. You're all going to get at least 90% here, okay? Your letter grade will not be hurt. It's a way for me to help students if they participate and engage well. That's the bottom line. Like if you're a grade borderline case. Okay, but you're not going to fail the class because of class participation, okay? Because you're getting at least 90%, right? It's supposed to help you. Okay, I don't expect a reverse curve. All right, so like 89% is an A. Although if you get like 885, then I might consider your participation, right? All right, question so far. That's the grading scheme, homework and class participation. Plus, I'll discuss extra credits soon. Any questions? Any questions? I will slow down as we go to the math a bit. Okay, you're reading the syllabus. All right. Academic integrity, no cheating. Although cheating on the homework, what is that? Well, collaboration outside of class is encouraged. I encourage people to work in groups. That's great. I remember some students, some were great at algebra, some were great at trig, and they made great groups. But systematic copying is forbidden. Okay, and I'll notice that. In that event, I'll have to talk with you. Online resources should be used judiciously, and make sure that you're using them to enhance your learning. Hey, if you find a great a YouTube or Khan Academy video online, you're learning from it, great. Whatever it takes to learn, great. But don't email someone and ask, how do you do this? Okay, from scratch. You're here to learn, all right? It's pre-calculus. We're preparing you for calculus. I want to teach. You want to learn, right? Let's do it. I love teaching. I hope you love learning. And I love working with students. Okay, and again, the stuff from prior terms may not apply now. I could give you different homework problems, and the grading schemes could be different. Okay, some more stuff on academic honesty. Okay, come to class with, well, internet access, obviously. Okay, you know, have your homework handy so we can talk about it, right? Because it's 85% your grade, right? I expect people to use a scientific calculator. Okay, graphing calculators do too much for you. Some paper and a pencil. We might do some stuff in class. It's your responsibility to add, drop, or withdraw. Okay, so don't expect me to drop you for whatever reason, right? Make sure you know your own status in the class, and remember the deadlines. Okay, and late drops may not be accepted necessarily. They may not be as liberal as in the spring. Instructor absence. Do you need this class? Go to assist.org and you can see if you even need this class. That talks about possible requirements for your major, right? Do you any example for the homework paper? Well, I mean, you know, like section 0.1, write your work down. So basically, you want to follow the models in my examples and in my, maybe in my exam solutions, maybe. But no, it's as you normally expect to do homework. Well, the solutions, you know, look at the work I do in class. All right, look at the work I do in class. And if you're not sure, come to the homework sessions and we'll talk about it. Per chapter, well, the chapters are of various lengths. Some are kind of short, some are very long. Okay, you can read over the official stuff here. Basic journeys, again, some services for students like veterans, for example, or assistance with housing and food. Notes and class contacts, again, look to each other. Is there homework? Okay, there's no, homework will not be due until September. We'll talk about it, but keep up. It's up to you to not procrastinate, all right? But I'll tell you how far to go. Remind me if I forget. Alex, review and extra credit. Up to 25 points, so it can help your grade. Okay, 6-week license, but you can renew it or get longer licenses. I'll email the class code within the next 48 hours. All right. Now, the Alex extra credit is for chapter 0, which is the hardest part of the class. It's mostly review. Do you remember how to factor? Do you remember real numbers? Right. And don't procrastinate, because sometimes Alex punishes procrastinators. I also have other Alex classes you can email me about, but chapter 0 is the one you get extra credit for. So many students need to firm up their factoring and all that stuff. Chapter 0, it's a hard chapter, lots of stuff in it. Okay. I think Safari's getting better, but Chrome is still supposed to be better. Okay, so you can get up to 25 points extra credit. Although you can, you know, if you don't quite make it to 90%, you can make it. You can still get partial credit. Okay, and don't cheat the system, because you'll end up doing more work. It's an AI system. It wraps around your brain, okay? There is nothing random in this class, okay? My homework problems are carefully designed. You're gonna learn a lot from them, all right? Alex, it's an AI system, a great AI system that helps you learn. I had this one student, my best student one semester, told me, he ended up with like 96% of the class. And he told me, Ken, I don't know if he said dude, but he said, Ken, when I started this class, like chapter 0, the Alex stuff, I didn't know any of that stuff. But that student did Alex, that student worked and engaged and ended up with the highest grade in the class. You can do it from scratch. Now, he was very smart. Okay, he was a very, very talented and talented guy and all, but you know, you can do a lot from scratch. Alex, again, okay, it's a computer software system that basically gives you sequences of problems. Can you do this problem? Answer it. Got it wrong? It'll give you some hints. Again, you don't have to do it in this class. You can still get an A without it. But it's an AI system that it's not random problems. It's a carefully designed sequence of problems, and it depends whether you get them right or wrong. in terms of where it goes with you. Oh, well, it should help you on the chapter 0 homework, but I had students go all the way to the due date, which is, I think, Monday, December 14th. It's the last day of our class. So even though it's the extra credit part is chapter 0, some people take all semester to do it. Bear in mind, you'd have to go beyond the 6-week license. You'd have to renew it or get a longer license. But some students do that. Now, don't procrastinate. If you wait too long, then you have to reassess, and then Alex might take you backward. But I do the best of. Okay, so there's like a midnight download, losing ground. Alex punishes procrastinators, so don't take long breaks. Students sometimes lose progress points. I had one student who said, Ken, I went from like 89% to 86%. I'm mad. But the thing is, I kept the 89% because in the midnight reports, I capture your best percent along the way the best I can. All right, so if you fall back a bit, I'll still keep your best of. But it's harder to go higher. I don't know if Alex is similar to WebAssign. I don't know WebAssign that well. I don't know Alex all that well either, to be blunt. But it's fairly user friendly. Internet technology. You're in my Zoom room. Make appointments. Okay. It's implied that you're consenting to being recorded. Sometimes I will turn off the recording, but if you say something or even potentially chat, I have the right to publish the chats. I don't expect to, but I have the right to publish them. So you have consent to being recorded. You can chat privately with me as well, or other students. Okay. Feel free to chat with me. YouTube has my pre-recorded lecture videos. I'll try to post homework and class sessions where possible, although again, students might want to be shy. Canvas, a few things, discussion board, NetTutor. The very tentative schedule. All right. And this should stick, actually. I've done this class many years, though not online. Okay, so chapter 0. I'm going to finish the material 2 Thursdays from now, August 27th. The following Tuesday, I'll start chapter 1, but then I'll start talking the homework with you, all right? And then we're going to have, well, I'll continue with chapter 1, and we'll have more time on homework, a bit over an hour, Thursday, September 3rd. That's a good time to ask me questions about the homework. Then it'll be due midnight, the end of Friday, September 4th. The homework for chapter 0 only. It makes sense to do Alex by then, but you can do Alex all the way through December 14th. So this is the scheme, tentative scheme. It should stick. Those big homework sessions in boldface, that's where I used to have exams. Any questions? Any questions? Feel free to keep chatting at me. All right. Let's begin with the material. All right. Again, feel free to chat at me. All right. Even though I'm talking in the lecture, feel free to chat at me. Here we go. Oh, I got to go to my my YouTube videos, my playlist. I got to go to my playlist. All right. The playlist has the appropriate order. All right. I am recording. Yes, I am. All right. So here's my playlist for this week. I organized by class and week. We got 9 videos here. Sometimes I have some goodies here. Let's start here. CC, please remind me to close caption if I forget. Here we go. Feel free to keep chatting at me.
Hi, everyone. Welcome to Pre-Calculus. My notes start off with a table of contents and a notation guide, which can be very helpful.
Can you hear it?
We're going to start now with chapter 0, which deals with preliminary topics. Now, chapter 0 sounds easy. It's the hardest chapter of the whole class for almost all the students because it's a mass review, and then we throw you up to the higher levels. We're going to start off today with the first 5 sections. All right. In 0.1, we're going to review sets of numbers. So what's a set? A set is a collection of objects called the members or elements of the set. In a Venn diagram, we often draw a set using some sort of circle or oval, and we can denote the elements of the set or represent the elements by little dots here. So for example, in the set of integers, which we'll talk about later on, maybe this dot represents 1, this represents 2, this represents 3, and so forth. And these are elements or members of the set Z, the set of integers. This is also a set. This here denotes the empty set or null set, which is the set consisting of no members. Sometimes when you solve an equation, there are no real solutions, and the solution set is the empty set or null set. Later on, I'll talk about the idea of subsets, but let's get right to it. Let's talk about these sets of numbers. 1, 2, 3, 4, and so forth. They're elements of Z, but they're also elements of Z plus, more precisely. By the way, we write Z either boldface or with a double bar that's referred to as blackboard bold. Z plus is the set of positive integers, and it consists of, so the set Z plus, grab this over here, here's Z. I can go over here. So Z plus consists of the following set: 1, 2, 3, and so on. That's the set of positive integers. Z, by the way, comes from the German word Zahlen, which means entire. For example, if you buy eggs at a grocery store, you normally buy a dozen, but you could buy 1 whole egg, 2 whole eggs, and so forth. Sometimes we refer to counting whole or natural numbers, but there's a lot of confusion as to which sets contain 0 and which ones don't. So I don't like to use those terms too much. All right, well, after the positive integers, what other numbers do you learn about? You learn about the negative integers, Z minus. Okay. So Z minus would consist of -1, -2, -3, and so forth. And then together with this super magic number of 0, and books have been written about 0, they don't cost 0, but books have been written about 0. Put them all together and you get Z, the set of integers, which consists of the positive integers, 1, 2, 3, and so forth, the negative integers, -1, -2, -3, and so forth, and also 0. Now let's say that we want to go beyond the set of integers. That's when we start making fractions. Then we can think about this new set, Q, the set of rational numbers, ratios of integers. This is the set of all numbers that can be written in the form integer over an integer that's not 0. Remember, it's always illegal to divide by 0. So for example, fractions such as 1/2, 1/3, this ugly thing, -823 over 9,900. And even 7, because 7 can be written as the fraction 7 over 1. Every integer is a rational number. And by the way, one comment about that. Because every integer is a rational number, we can say that Z is a subset of Q. So that goes back to what I had up here, right? Let A and B be sets. A is a subset of B, and that's denoted by this over here, when every member of A is also a member of B. So for example, if this oval represents A in our Venn diagram, and this oval represents B in our Venn diagram, then A is a subset of B. Every element of A is also an element of B. We assume that B includes everything inside the big oval here. every integer is a rational number because every integer can be written as itself over 1. Z is a subset of Q. Every integer is also a rational number. Q, by the way, comes from quotient, right? If you divide an integer by a non-zero integer, you're taking a quotient of integers, you get a rational number. We often think of these as fractions of integers, positive or negative or 0. We can also think of them in decimal form. So we can think of the rational numbers as the set of numbers that can be written as finite or terminating decimals, such as 1/2, which is equal to 0.5 or 0.5. The 0 here is optional. Now this is a terminating or finite decimal that indicates that 1/2 is a rational number. 0.5 is a rational number because it can be written like this, 1/2. 7 is also terminating. But a rational number could also be a repeating decimal. For example, 1/3 can be written as, well, 1/3 is exactly 0.3 bar. This is a repeating bar here. And this number is, in decimal form, 0.3333333, and so on, forever and ever. So a decimal number that can be written in this repeating fashion is also a rational number. This decimal number can be written as 1/3. It's a rational number. So the rational numbers include numbers like these. Numbers that can be written as nice fractions or whose decimal representations either terminate or go on forever in a repeating fashion like this or this, for example. So beyond the rational numbers, let's say that we have a number that can be written in decimal form, but it doesn't terminate, or you couldn't use a repeating bar. Then we get to the world of R. R is a set of real numbers. Basically, if you take any number that can be written as a decimal with a decimal point, a finite number of digits to the left, and any number of digits to the right, you get a real number. Examples include these guys. Pi, which is about 3.14, it's 3.14159, and so on and so forth. Sometimes people memorize digits of pi if you have no life. There was a fellow in 60 Minutes who thought of the digits of pi in terms of colors. But there is no repeating pattern, and it does not terminate as a decimal. The square root of 2 has the same feature. This number has the property that when you multiply it by itself, you get 2. It's 1.414, It does not terminate or repeat. Now, we can indicate the set of real numbers using a real number line. Any real number will correspond to some point on this real number line. All right. Beyond the set of real numbers, we have these. C, the set of complex numbers. Actually, every real number is a complex number. Hey, 0 is a complex number. So you've been studying complex numbers all your life. But the ones that go beyond the real numbers are the imaginary numbers. Things like I and 2 plus 3i. We're going to see these old friends of ours starting in chapter 2. For right now, in chapter 0 and chapter 1, we're going to keep it real.
Okay, so that was video 1. Okay, and I do have my notes up as well. Any questions? Any questions? Okay, I can pass my notation guide. Any questions? Now, you know what? Right now, I'm gonna pause the recording. Remind me to resume at some point. Closed caption, please remind me.
Hi, everyone. Let's go back to the idea of a set A being a subset of a set B, denoted by this, A, and then this sort of C-looking symbol with a bar underneath, B. A is a subset of B. That means that every element in A is also an element in B. It's assumed that B contains all the elements inside the big circle here. including in this case, all the elements of A. Now, if there are elements in B that are not elements of A, then that means that A and B cannot be equal sets, which means that we can remove the bar there, and we can then say that A is a proper subset of B. So we just need that C symbol there. So every element of A is also an element of B, but they're not equal sets. So now we can talk about the proper subset relationships between these sets. So for example, Z plus, the set of positive integers, 1, 2, 3, 4, 5, 6, 7, and so forth. The set of positive integers is a proper subset of the set of integers. Z, the set of integers, contains Z plus, but also numbers like -1 and 0. In turn, Z is a proper subset of Q. Z is a proper subset of Q because every integer is a rational number. Remember, you can put these guys over 1 and you get a nice fraction. But not every rational number is an integer. 1/2 is a rational number, but it's not an integer. So these are not equal sets, and we have a proper subset relationship here. Likewise, Q is a proper subset of R. Every rational number is a real number, but not all real numbers are rational. Pi, for example, is irrational. The square root of 2 is irrational. Likewise, R is a proper subset of C. All real numbers are complex numbers, but there are imaginary numbers, like I, that are complex but not real. R is a proper subset of C. And there are sets that are even, in a sense, larger than C. Quaternions, octonions, and I'll send an email about that later on. But C is the biggest set we'll deal with in this class. We do nudge a little bit into quaternions a little bit with vectors, but that's later on. Okay. Next up, we're going to talk about set notation. How to parse symbols like these.
All right, any questions? Any questions before we go on? Any questions? That was a short one. Sometimes I'm afraid to go on before I make a mistake. Any questions? All right. Oh, raising hand. Okay, let me. Well, go ahead and chat. Yeah, go ahead and chat. You don't have to raise your hand. Go ahead and chat.
Sorry.
Or vocally. You can do it vocally. Okay. Orally. Okay.
Sorry, it's just easier for me this way. But the stuff you're working on, I'm sorry if I missed something, but the sheet you're going over, is that available to us?
Yes, it's on my website. Under notes for quiz 1A. It's chapter 0.
Cool.
All this stuff is online. Absolutely.
Cool.
PDF form.
Thank you.
Yes. Oh, yes, I'm sure that's a big relief. Otherwise, I'd be writing like crazy. I'm doing this for you because I remember when I was a student, I learned how to write fast. I didn't learn anything in class. All right. Any other questions? Any other questions? All right.
Hi, everyone. Back to sets. This, by the way, is called a Venn diagram, which is a graphical way of representing a set. Venn diagram, a graphical way of representing a set. So, for example, 0, -1, and 7 are elements or members of the set of integers. Z is a subset of Q, and so forth. Let's talk about set notation. So this sort of curvy E denotes in or is in. It denotes set membership. So for example, 7 is a member of the set of integers. 7 is in Z. In plain English, 7 is an integer. Okay, 7 is inside the disk for integers. If you slash something, that tends to negate the operator. It tends to mean not. So this sort of epsilon symbol with a slash through it, that denotes is not in. 1/2 is not an integer. 1/2 is not a member of Z. 1/2 is not an integer. This is more rare, This backwards E guy denotes such that in some settings. We don't use that too often. In fact, later on, we tend to use a bar for that, for such that. These two guys you see a lot in calculus theorems. The upside down A, the universal quantifier, denotes for all or for every. So for example, in a calculus theorem, you might see something like this. For every x in the set of real numbers, da 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 da. In other words, for all real numbers x, for all real numbers x, we say that this statement is true. For example, for all real numbers x, it's true that x is less than x plus 1. That's true for all real x. The backwards E is the existential quantifier, and it means there exists or there is. These you find in existence theorems. Don't worry, I'm not going to have you parse things like this in our class, but you do see these kinds of theorems in calculus. Blah, 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 there exists a real value y such that da, da, da. So here are some set notations. Next, we're going to talk about subsets of real numbers.
And we're going to talk about infinity. And while we're at it, this is a nice fun time for me to show some videos because I like to break things up. All right, I'll pause things now. So my video's on infinity. Oh, hold on a second.
Hi, everyone. Remember R, the set of real numbers, which we can represent graphically by the real number line. Now, we can associate this right arrowhead with the idea of infinity. Remember that symbol. Infinity, which is denoted by this lemniscate, is a quantity that is greater than any real number, even 10 billion or 10 trillion. So infinity, bear in mind, is not a real number. It's the idea of something that's bigger than any real number. Likewise, negative infinity is a quantity that's lesser than any real number. And we tend to associate negative infinity with the left arrowhead over here on the real number line. We're going to need infinity and negative infinity as we describe and represent sets or subsets of real numbers. So let's say that we want to represent a subset of real numbers. Well, if we just care about a couple of real numbers, like 1 and pi, we can just separate them with one or more commas and surround them with braces. I know students have a hard time drawing these things, but you'll get used to them. However, we often want to deal with intervals on the real number line. An interval corresponds to a connected or unbroken piece of the real number line. A piece, a connected piece of the real number line. A bounded interval, such as this one here, a bounded interval has finite, a bounded interval has finite length on the real number line. It's trapped between a couple of real numbers. An unbounded interval has infinite length, and it shoots off to either positive infinity or negative infinity. An open interval excludes its endpoints. A closed interval includes its endpoints. And you can have various combinations. So for example, consider the set of all real numbers x such that x is strictly between 3 and 5. This leads to what we call a bounded open interval. It's bounded because we're only considering real numbers that are trapped between a couple of real numbers, and it's open because this interval does not include its two endpoints, the 3 or the 5. These are referred to as strict inequalities. We exclude the 3 and the 5. If we wanted to include the 3 or the 5, we put bars. These are strict inequalities. Now, we want the set of all real numbers x that satisfy this compound inequality. In set builder form, which involves these braces here, we want the set of all x in the reals such that, so the vertical bar here or the colon here can represent such that x is strictly between 3 and 5. In graphical form, we want all the real numbers on the real number line that are between 3 and 5. However, because we exclude the endpoints, the 3 and the 5 themselves, we put open, hollow endpoints at the 3 and the 5. By the way, this interval doesn't just include the number 4. It includes 3.5, 4.99, and also a very famous real number, pi. It's not just 4. There are infinitely many real numbers in this interval. In interval form, we write this as 3 comma 5 surrounded by parentheses. We use a parenthesis if we exclude the endpoint. All right. Now what happens if we close this off, if we include the endpoints? Then we have a bounded closed interval. The set of all real numbers at x such that x is weakly between the two numbers 3 and 5. So 3 and 5 are fair game in this set. They're elements of this set. In set builder form, this is the actual set. In set builder form, it's the set of all x in the reals such that x is between 3 and 5 inclusive. The set includes 3 and 5 themselves. In graphical form, you can see this barbell, where instead of hollow endpoints, we have solid endpoints at 3 and 5. We fill in the dots. In interval form, we don't have open parentheses, we have closed brackets. The 3 and the 5 are included in this set. So these are 3 different representations of the same set. It includes 4, 3.5, pi, and also 3 and 5 themselves. It's a bound closed interval. This time we include the endpoints at 3 and at 5. Let's look at this whole gallery of intervals. I'm glad I don't have to write this on a chalkboard. Okay, you can have intervals that are bounded and half open and half closed. For example, this interval includes 3 and excludes 5. So we have, in interval form, it looks like that. Here, it's vice versa. You exclude the 3 and include the 5. Here, we have an unbounded interval, open interval, all real numbers greater than 3, shooting off towards infinity. Here, we include the 3. We have a bracket instead of a parenthesis. By the way, you always put a parenthesis next to infinity. Infinity is not a real number. You never include infinity in these intervals. So you always put a parenthesis next to infinity or negative infinity. Over here, where these intervals are shooting off unbounded to the left, here we have all real numbers strictly less than 3, open interval. Here, we close it off at the endpoint. We include the 3. R, the set of all real numbers, can be represented by the entire real number line. It's good to indicate where 0 is and also a non-zero number, but we often get sloppy with that. We color the whole real number line. You should remember that this is the interval form for R, the set of all real numbers. Parenthesis, negative infinity, comma, we want everything in between, infinity. By the way, R and also the empty set are both closed and open at the same time. It's kind of weird. All right. Next up, we're going to talk about operations combining and manipulating intervals of real numbers. Next time.
Any questions? Because it's been a long time for a lot of you. One of my best students one semester said this is the hardest stuff. By the way, the numbers have to be in order. If you switch the 5 and the 3 here, you get the empty set. You have to follow the real number line left to right. Okay? Okay, negative infinity always has to be on the left, never ever on the right. Any questions? Any questions? Oh, okay. Now, yeah, question. You can unmute. Question. All right. Now, I want to go back up. I'll go to my notes. I want to go over here. Okay. The open interval between 3 and 5. Now, if you were to ask a naive student, how many numbers are in here? How many numbers are in this set? How many numbers are in this set? The answer is infinitely many, right? You have pi, you have 3.99, 4.92, and so forth. Infinitely many numbers. It's not just 4. It's not just 4. Okay, although here's a nice joke from a film, Dumb and Dumber 2, a related idea. Oh, wait, whoa. Hold on. I gotta pause it. Okay, any questions before we go on? Sets of numbers. These are subsets of R. All right. By the way, one note, you should from time to time check my thing here because sometimes I have corrections down here. I make mistakes sometimes. I have corrections down here. I don't know of any for this chapter yet.
Hi, everyone. Let's perform operations on sets. Let's say that I'm the president of a fraternity. It takes me back. And our fraternity will be throwing a party. In order to be allowed into our party, you have to bring food or beer. So let's say that set A is the set of people who come to our party with food, and set B is the set of people who come to our party with beer. We allow both sets of people in. The union of the set A and the set B, which consists of all elements in one or both sets. All members are invited from these two sets. So, let's say that this box here represents the set of all students at the college. Set A is a set of students who come to our party with food. Set B is the set of students who come to our party with beer. In order for us to let you in, you can bring food or a beer, or both. It's okay to bring both. It's an inclusive or. It's not exclusive or. We're not mad at you if you bring both. An exclusive or is like at a restaurant, super salad. That's an exclusive or. You can't have both. With inclusive or, and or is assumed to mean inclusive or, it's okay to have both. It's okay to bring both food and beer. But who's invited to the party? Everyone who brings food, also everyone who brings beer, and of course, the people who bring both. So this shaded in region represents A union B. Everyone who brings food or beer is invited in. This, by the way, is the professional way to represent or, that little V. Now, on the other hand, what about an intersection? So let's say that in order to be invited to the party, you have to bring food and beer. Food and beer. So let's say that this is the set of all students at the college. Here's a set A, the students who bring food. Here's a set B. Whoops. Here's a set B, the students who bring beer. Lots of people bring beer. But who's invited? The people who bring food and beer. That's only going to be the people in purple here, inside this lemon wedge here. I better color it out here. The people inside that lemon wedge there, right? So in order to be invited to our party, you have to be in A intersected with B, the intersection of A and B. You have to bring food and beer. This is the professional way to represent and, the tenth. Okay, so remember, a union means that we include everyone in both sets. An intersection means we take the overlap. You have to bring food and beer. All right, so let's consider this union of intervals. All right, so this set here turns out to represent a union of intervals. This is the set R, the set of all real numbers, excluding the two numbers 1, and pi. So this is written in set difference form. The slash here indicates the subset of real numbers we exclude from the set R. We want all real numbers except for 1 and pi. In set builder form, we want the set of all x's in the reals such that x is not 1 and x is not pi. If you're anyone except for these two numbers and you're real, we want you. You're in the set. Now, before you write the interval form, even without asking you, you may want to write the graphical form. Graph this set. So we basically shade in the entire real number line, except we put open hollow circles at the 1 and the pi, because these are the two real numbers that we exclude. We pluck out these points on the real number line when we draw our set. So in interval form, what do we want here? It's like Converse. We have a left wing, a middle piece that's small, and a right wing. All right. This is here a union of three intervals. The left wing, parenthesis, negative infinity, comma, 1. We exclude the 1. We kind of skip over the 1. Anytime you hop over one or more real numbers, you need that union symbol. For this middle piece here, the barbell, we want the real numbers strictly between 1 and pi. It's an open interval here. We exclude the endpoints, the 1 and the pi. For the right wing here, we want all real numbers greater than pi. We exclude pi itself, but we want all real numbers greater than pi. So we stretch out towards infinity. Remember, we always put parentheses next to infinity and negative infinity. A union of three intervals, a union of these three connected pieces. That's the interval form for the set. Remember, these three are representations of the same set, the set of all real numbers, excluding 1 and pi. All right. So let's say that we have two intervals here. Let's say that this represents the set of people who bring food, and this interval represents the set of people who bring beer. All right. How do we take the union of these two sets? So this is a situation where you're invited to the party if you bring food or beer. So which numbers do we color in purple on this real number line? If you're in purple in here, it means that you're invited to the party. The purple people here bring food. The purple people here bring beer. Who's really invited to the party? Well, the negative numbers and 0 and 1/2, let's say, they're no good. They're no good. They don't bring anything. They're no fun. So they're certainly not invited to the party. They can't come in. What about 1? Well, again, doesn't bring anything. Okay, 1.1, 2, 2.9. What about those guys? No, those guys are good. Those guys are good. 1.1, I should do it in blue, let's say. 1.1 brings food. That person's good. 2 brings food. That person's good. Okay, 3 brings both. That's good. Pi brings both. 4 brings both. 5 doesn't bring food, but does bring beer. And the numbers greater than 5, although they don't bring food, they do bring beer. So basically, any number that's purple on this line or on this line will be purple on this third line over here. So to simplify the union, we want all the real numbers greater than 1. We want to write the result in simplest form. All real numbers greater than 1. Over here, the intersection. Remember, for intersection, think overlap. Think overlap. All right. Here, remember, for B, to be allowed into the party, you have to bring food and beer. Food and beer. Okay, so let's take a look at the people who bring food, the people who bring beer. Are they invited to the party? These people bring neither. They're no fun. Not in the party. These people, like 1.1, 1.2, and 2, they bring food, but they don't bring beer. So they're not allowed because they don't bring beer. The lowest number that's allowed into the party, the least number that's allowed in, is the 3. 3 brings food and beer. That's good. High is good. 4 is good. 4.9 is good. 4.99 is good. 5, however, does not bring food, and we're hungry. 5 does not bring food. 5's out. So is 5.1. So 6. So are all these numbers greater than 5? So the overlap of the purple piece up here and the purple piece over here is going to be the barbell over here, where we include the 3, but we exclude the 5, like so. By the way, if you're going to play this game, make sure that your number lines are positioned the same way. The zeros are lined up and they're scaled the same way. The 1s line up, the 3s line up, the 5 lines up, 5s line up, and so forth. Union, if you're on here or in here, you're in. Intersection, you have to be on here and here in order to be in. Next up, let's be trained to think logically. Next time.
All right. So, yeah, I realize I can't update my lectures to the pandemic. That's just sad. What, Uber Eats? Uber Eats, maybe? Okay. All right. So that's 0.1. Any questions before we go on to 0.2 on logic? Any questions? Any questions? All right.
Hi, everyone. Your significant other may have accused you of not thinking logically. Well, prove them wrong. Section 0.2 on logic. A proposition is a statement that is either true or false. For example, I get an A in the class, or I pass the class. P and Q could be propositions here. If P then Q can be written like so, with an arrow here. If P then Q. P here is called the hypothesis, assumption, or condition. Q is a conclusion. Now this statement, if P then Q, could itself be true or false, as we'll see. If we know it to be true, we sometimes use a double bar arrow, and we might say that P implies Q. Now, if P implies Q and Q implies P, I'll skip all the way to here. If P implies Q...
Hey, you know what? I just realized something. This is running 13 minutes. It's about time for a break. You wanna take a break now? Yes. Come on, you wanna take a break, right? Let's take a break. I'll do this. I'll replay this later. Let's take a break now. 10-minute break. Okay, I have 8:19. I'll see you folks at 8:30. All right, so I'll see you folks at 8:30. Now remember to mute. Before you go to the bathroom, please mute. All right. Mute. All right, so let's start again. Welcome back.
Hi, everyone. Your significant other may have accused you of not thinking logically. Well, prove them wrong. Section 0.2 on logic. A proposition is a statement that is either true or false. For example, I get an A in the class, or I pass the class. P and Q could be propositions here. If P then Q can be written like so, with an arrow here. If P then Q. P here is called the hypothesis, assumption, or condition. Q is a conclusion. Now this statement, if P then Q, could itself be true or false, as we'll see. If we know it to be true, we sometimes use a double bar arrow, and we might say that P implies Q. Now, if P implies Q and Q implies P, I'll skip all the way to here. If P implies Q and Q implies P, then they imply each other, and we have logical equivalence, meaning both have to be true or both have to be false. Many definitions can be thought of as these: if and only if, or IFF statements. For example, 2x equals 6, if and only if x equals 3. If you're solving a math problem in an Algebra 1 class, you often write a sequence of equations and they're equivalent in the sense that you can reverse the arrow. And these are all true or all false. All right. Let's do an example. Consider this if-then statement. If I get an A, so that's proposition P, then I pass. I pass is proposition Q. P can be true or false. Q can be true or false. So P here is the hypothesis, assumption, or condition. Q is the conclusion. Okay, now, first of all, is this statement true or false? If I get an A, then I pass. Well, that statement is true. If you get an A in the class, then you pass. But now consider the converse of this. The converse of the if-then statement, if P then Q, is the statement if Q then P. If this is if P then Q, write the statement if Q then P. What is the converse of this statement up here? What's the converse of that statement up there? The converse will be, if I pass, then I get an A. Is that a true statement? If I pass, then I get an A? No, because we can think of a counterexample. A counterexample. A counterexample corresponds to
Can you hear me? Yeah.
where the hypothesis is true and yet the conclusion is false. Can you think of a situation where you pass and yet you don't get an A? Can you think of a counterexample? Well, yeah, you can get a B or you can get a C. And these are both counterexamples where you pass but you don't get an A. And if you have counterexamples, then that means that this statement overall is a false statement. Overall, it's a false statement. Big ol' F. If I pass, then I get an A. That's a false statement. It's true that some people who pass get an A, but as an if-then statement, this is false, because the hypothesis does not guarantee the conclusion. All right. So sometimes the converse is true. Sometimes the converse of a true statement is true. Other times it's not. So you have to be careful not to mix these up. In an if and only if case, you could mix them up. You can associate these things together, but sometimes the arrow matters. I'll give you a more algebra example. X equals 2 implies that x squared equals 4. I think you would agree that if x equals 2, we know that x squared has to be 4, okay? This is a true implication, a true if-then statement. That's why you have the double arrow here, double bar arrow. But consider the converse. if x squared equals 4, then x equals 2. Does this imply that? If x squared is 4, x could be -2. That's a counterexample. That would cause the top to be true, but not the bottom. So x squared equals 4 does not imply that x equals 2. And overall, if you say x squared equals, if you say if x squared equals 4, then x equals 2, that would be a false statement. If you were to say, well, if you were to say if this, then that would be a false statement because we have a counterexample. This is a false if-then statement because there's a counterexample. So be careful. There are some situations where you cannot reverse the arrow. And these are often situations where we have to check our solutions. For example, this is related to the idea that if you have a radical equation, and if you square both sides of an equation, then in the end, you have to check your solutions. All right, anyway. So the converse of a true if-then statement could be true or could be false. Now consider another example. Here. Consider this. A Jerry Springer example, if you remember him. If Pat is a daddy, then Pat is a man. That might be a bit un-PC, but let's accept that. If Pat is a daddy, then Pat is a man. Let's say that's true. What would the converse say? What would the converse say? The converse would say, if Pat is a man, then Pat is a daddy. Are all men daddies? Am I going to get a surprise in a couple of weeks? This is a false statement. This is a false statement. So this is a case where, again, the converse of a true statement is false. All right. So let's say that the original statement goes, if P, then Q. Here's the original statement. If P, then Q. For example, remember the statement we talked about earlier. I'll shrink this. If I get an A, then I pass. If I get an A, then I pass. P says I get an A, Q says I pass. Well, remember, what's the converse of the statement? If Q, then P. The inverse is if not P, then not Q, where you negate the hypothesis and the conclusion. We're not going to deal with that. I'm going to talk more about the contrapositive. So what's the contrapositive of if I get an A, then I pass? The contrapositive of if P, then Q is if not Q, that's what the tilde means. If not Q, then not P. This also represents not. This and also that, these represent not. So for contrapositive, what do? You switch and negate the hypothesis and the conclusion. Switch and negate. Switch and negate. Okay. You switch P and Q and you not both ends. What is the contrapositive of if I get an A, then I pass? Well, first off, remember the converse is if I pass and I get an A. We know that's false. The original statement is true. The converse was false because we found counterexamples. You could get a B or a C. But now what's the contrapositive? The contrapositive is going to be, okay, so again, here's the original. Here's the contrapositive. By the way, the inverse just negates the two ends, the two propositions. The contrapositive says, switch and negate. if I do not pass, then I do not get an A. If I do not pass, then I do not get an A. Is that a true statement? If I tell you you don't pass, is it possible that you can get an A? No, it's impossible. This is a true statement. If you don't pass, you don't get an A. Now, that's not a coincidence, because we have what I call the contrapositive theorem. If an if-then statement is true, such as this one, if I get an A, then I pass, then the contrapositive must also be true. If I do not pass, then I do not get an A. This Venn diagram might be helpful. Okay. So again, if you get an A, then you pass. If you're in this disk, if you're in the inner disk, you're in the outer disk. What does the contrapositive say? The contrapositive says, if I do not pass, then I do not get an A. If you do not pass, then you're out here somewhere. Then is it possible that you're in here, that you get an A? No, that's impossible. You do not get an A. If you're not passing, if you're outside the outer disk, there's no way you're inside the inner disk. If you're not passing, there's no way you're getting an A. The contrapositive theorem. If an if-then statement is true, the contrapositive is automatically true. Now, this is very valuable. Let's say that I give you 10 different math theorems. All of them are if-then statements. Really, by the contrapositive theorem, you have 20 if-then theorems, because you can take the contrapositive and get another theorem that's true. So I've doubled your theorems. You should pay me. All right. For an if and only if statement, let's say this is true. If I get an A, B, or C, then I pass, right? Well, the converse is also true. Okay. And if the original statement and the converse are both true, well, that means we have an if and only if statement that's true. Okay. The contrapositives of both are true. They're all true. So for an if and only if statement, okay, if you take this true statement, if it's really an if and only if statement that's true, then the converse is true, the contrapositive is true, the inverse is true, all those guys are true. So you can associate P with Q. You have complete equivalence. We can say you get an A, B, or C if and only if you pass. You have equivalence. Again, dictionary definitions are typically if and only if statements. Runner, noun, one who runs. In higher math, they talk about necessary and sufficient conditions. Use your common sense. You can parse those logically. All right, I hope you learned how to think logically, and you can now tell your significant other to go away. You can think logically now. All right, until then.
All right. So let's meet Pat, maybe. Maybe this is Pat. Actually, maybe not Jerry Springer. I'm actually thinking more Maury. Oh, whoa, 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 whoa. All right. Next up, you might be surprised by this next topic. Any questions, by the way? All right.
Hi, everyone. When I used to grade calculus exams, I was always shocked by how bad my students were at rounding off their final answers appropriately. So section 0.3 on rounding. So if using a calculator, it might help to know how to use the memory buttons on your calculator so that you can keep and preserve decimal accuracy. Because if you round off too much in the middle, you can ruin the accuracy of your final answers. Now, remember that pi is an irrational number. Its decimal expansion goes on and on and on without terminating. So if your calculator says that pi is 3.14159265, that's only an approximation, and you should use the squiggles. Pi is about that much. That is not the exact value of pi. Calculators cannot give exact decimal representations for these kinds of irrational numbers over here. Now, in a math class, math instructors typically expect exact answers, and also decimal approximations if you're doing word problems. In a science class, they tend to deal with issues of measurement accuracy, and they tend to deal with approximate decimal answers. So in a math class, if an answer is pi, you better say pi, okay? And you should be prepared to give a decimal approximation as well. It's common knowledge that pi is about 3.14, but it's not exactly 3.14. Remember the squiggles. The squiggles here, this means is approximately or is about. Pi is about 3.14. It's not exactly 3.14. In a word problem, depending on the context, decimal answers might need to be rounded down, rounded up, or rounded off, depending on the nature of the word problem. And always put units such as feet, pounds, and so forth as part of your answer to a word problem. All right, rounding. Let's take pi. Pi is about 3.14159. Now pi, rounded off to the nearest integer, is just 3. So just scratch this all out. Pi to the nearest integer is just 3. The next digit here is a 1, which is a low digit, is less than 5. So pi rounds down to a 3. When you round off pi to the nearest integer, it rounds down to a 3. Now pi rounded off to the nearest tenth or to 1 decimal place is it 3.1 or 3.2? Well, the next digit is a 4, which is below 5. It's a low digit. So again, we round down to 3.1 because the 4 is a low digit. But what about pi to 2 decimal places or to the nearest hundredth? That's 3.14 because the next digit is a 1, again, a low digit. So we round down, we round off by rounding down to 3.14. Now to the nearest thousandth, or 3 decimal places, it's 3.141, not 1, but 2, because 5 is considered to be a high digit in the United States. 5 or higher, you round up. When you round off, you round up, in this case to 3.142. In Europe, they play an even odd game with the 5, but in America, if you see 5 or higher, then you round up. All right. Consider a number written in decimal form. To count the number of decimal places the number is written out to, count all the digits to the right of the decimal point. To count significant digits, or significant figures, you locate the leftmost non-zero digit and count it and all digits to the right of it. So by these rules, and by the way, we like to have numbers rounded off to the same number of decimal places if we're adding or subtracting. We like to use numbers written out to the same number of sig digs or sig figs if we're multiplying or dividing. Also with sig digs or sig figs, you could have different units like inches, feet, and miles and have roughly the same level of accuracy if you're using significant figures, the same number. Okay, consider this, 70.1230. How many decimal places is this written out to? How many sig digs or sig figs is this written out to? Well, let's count the number of decimal places. You count all digits to the right of the decimal point. 1, 2, 3, 4, including the 0 here. Remember, if you're writing down that ending 0, that trailing 0, it means that we're assuming that we have the right to write that 0. We do have that level of accuracy. This is written out to 4 decimal places. There are 4 digits after the decimal point. But for sig digs or sig figs, we start with the first leftmost non-zero digit, count it and everything to the right. 1, 2, 3, 4, 5, 6. We have 6 sig digs or sig figs. Right. Now, what about this? The 0 to the left of the decimal point is optional, unless there are non-zero digits to the left of it. Like the 7 over here. But here the 0 is optional. 0 point, or just point, 001020. How many decimal places and how many sig figs is this written out to? How many decimal places? Okay, you start at the decimal point. You count these, 1, 2, 3, 4, 5, 6. So 6 decimal places. I sound like the count from Sesame Street. Ha ha ha. 6 decimal places. But you don't include that 0 there. That's optional. But you do include this last one. We're claiming that level of accuracy. But how many sig figs? How many sig figs? We start at the first non-zero digit. That's the 1 here. 1, 2, 3, 4. Again, you count that 0 at the end. 4 sig figs. And if you use scientific notation, you would put these 4 digits. So you can write this number as 1.020 times 10 to the negative 3. The negative 3 tells us how to move this decimal point. You move this 3 places to the left to construct this number here. Right. If the exponent is positive, you move to the right, and you get a bigger number, a greater number, if it's positive. All right. Next up, absolute value. You think you know absolute value, and you don't, but you need it for calculus. Next time.
All right. Any questions about this rounding? Because a lot of people in calculus, they don't round properly. All right. Any questions? Let's keep chatting. All right. Let's go on.
Hi, everyone. Section 0.4 is on absolute value and distance. Absolute value is a topic you think you know, but you don't, and you really do need to know it for calculus early on. Now let's start with an example to make you feel comfortable. What is the absolute value of 7? Well, it's 7. What's the absolute value of 0? It's 0. And what's the absolute value of negative 3? It's positive 3. So a naive student might say, oh, to take absolute value, I basically copy the number. Unless there's a negative sign in front, then I zap it. I remove it. That's a naive way of looking at it, though. And I'll explain why in just a moment. First of all, what is absolute value? Well, we can interpret it in terms of distance. So for example, why is the absolute value of negative 3 positive 3? Let's go down here. Interpreting absolute value as a distance. The absolute value of A, where A represents a real number, is the distance between A and 0 on the real number line. By definition, distances cannot be negative. Absolute value cannot be negative. Oops, let's get a red color here. Absolute value cannot be negative. Distances cannot be negative. So if you look at the real number line, here's 0. Both 3 and negative 3 are 3 units away from 0. So for that reason, the absolute value of positive 3 is still positive 3. The absolute value of any positive number is itself. And the absolute value of negative 3 is also positive 3, because negative 3 is also 3 units away from 0, like the origin. So 3 and negative 3, notice these numbers are opposites. They have the same absolute value. In general, opposites have the same absolute value. So these are both true. So now let's go back and let's talk about the definition of absolute value using symbols. And it turns out to be a piecewise definition. You need to know this for calculus. The piecewise definition of absolute value. It's called piecewise because there are different rules for different values of A, the value you're taking the absolute value of. The absolute value of A, denoted by this over here, the A surrounded by the 2 vertical bars. The absolute value of A is A itself if A is positive or 0. In other words, if A is non-negative. That's a great word to remember. Positive or 0 means non-negative. If A is non-negative, is its absolute value is itself. The absolute value of a non-negative value is itself. So for example, the absolute value of 7 is 7. The absolute value of pi is pi. The absolute value of your SSN, your social security number, is your SSN. What is it, by the way? Daddy needs to buy stuff on Amazon. And the absolute value of 0 is 0. All right. Now this is going to look weird to you. The absolute value of A is its opposite. It's the opposite of A if A is negative. Now you might be looking at this and you might be going, wait a minute. So when I take absolute value, I'm inserting a negative or opposite sign if A is negative? And the answer is yes. Because let's think about this more carefully. Let's look at the absolute value of -3. Well, in fact, let's look at the rules overall. Right. So over here, so the absolute value of 7 is 7. Why is that? Because 7, if A equals 7, 7 is non-negative, so we use the top rule. The absolute value of A is A itself. So the absolute value of 7 is 7. The absolute value of 0. Well, if A equals 0, 0 is non-negative, so the absolute value of A is, again, A itself, because A is non-negative. We use the top rule. But now, what about the absolute value of -3? Let's type this out. Now, the absolute value of -3, if A equals -3, we take the bottom rule. If A is -3, we take the bottom rule. And the absolute value of A is its opposite. So the absolute value of -3 is the opposite of -3, which is +3. This makes sense because the absolute value of a negative number is positive. And we know that absolute value is either positive or 0. It's not negative. So again, the absolute value of a non-negative number is itself. The absolute value of a negative number is its opposite, which is positive. For example, in this case over here. Any questions about that?
Okay, seriously, any questions? Because a lot of people get confused by that. The whole concept of, wait, so the absolute value of A, the expression can contain that opposite sign? Yeah. Any questions there?
All right. So the absolute value of A, the opposite of A does not necessarily represent a negative value. If A is negative, then this thing here is positive. Not funny. Some properties of absolute value. The key thing is number 1. Absolute value is never negative. Again, it corresponds to a distance from 0. Some other interesting facts. Opposites have the same absolute value. Remember, in our example here, 3 and -3 have the same absolute value. 3, because these numbers are both 3 units away from 0. Opposites have the same absolute value. Also, and this comes down to the fact that absolute value is non-negative, the absolute value of a product is the product of absolute values, and the absolute value of a quotient is the quotient of absolute values, as long as you're not dividing by 0. So absolute value does break up across products or quotients, but not across sums or differences in general. All right. We talked about interpreting absolute value as a distance. The absolute value of A is the distance between A and 0. Oops, make this bigger. The absolute value of A, which can be thought of as the absolute value of A minus 0, is the distance between A and 0 on the real number line. More generally, the distance between A and B can be written as either the absolute value of B minus A or the absolute value of A minus B. Either will represent the distance between A and B on the real number line. So, for example, if you consider x and 3, all right? I don't care if x is to the right or the left of 3. I don't care if x is greater than 3, equal than 3, or less than 3, right? The distance between 3 and x, or x and 3, can be denoted by the absolute value of x minus 3 or 3 minus x. This is really convenient in calculus, because in calculus, we're interested in when two numbers are close to each other. And it doesn't matter which one is bigger, which one is smaller. So if you just want to know the distance between x and 3, and you don't care which one is bigger or which one is smaller, they could be equal even, then you can use either absolute value notation. For example, 7 and 3. If x is 7, all right, then your result's going to be is going to be 4, whether you plug in the 7 here or the 7 here. The end result is going to be 4, because the absolute value of 4 is 4. The absolute value of negative 4 is also 4. And why is that? Well, remember, opposites have the same absolute value. Opposites have the same absolute value. And I claim that b minus a is the opposite of a minus b. B minus a is the opposite of a minus b. I call that the opposite differences rule, or the switch rule. B minus a and a minus b are opposites. If you don't believe me, look at this. What is the opposite of a minus b? Well, we can distribute the negative 1. We get the opposite of a plus b. You can reorder the terms, and you get b minus a. The opposite of a minus b is b minus a. B minus a and a minus b are opposites. So for example, 7 minus 3 is positive 4, but what's 3 minus 7? It's negative 4, the opposite. 7 minus 3 and 3 minus 7 yield opposite values. In general, b minus a and a minus b yield opposite values, and therefore, they have the same absolute values. The absolute value of b minus a is equal to the absolute value of a minus b. So it didn't matter which order you wrote the 3 and the x in, around the minus sign, if you have absolute value on the outside. All right. So again, this comes up in calculus because you want to know if two numbers are close, and it doesn't matter which one is bigger, which one is small. In these pictures, here x is greater than 3, here x is less than 3. But either way, either of these two expressions will work, the absolute value of x minus 3 or the absolute value of 3 minus x. It doesn't matter who's bigger and who's smaller. It's very convenient. Again, these both represent the distance between a and b on the real number line. Both are non-negative. All right, next up, you should know these, rules of exponents and radicals. They're very closely related. Next time.
Any questions about absolute value? You have to nail that down solidly when you get into calculus, because these little salties can get you. I think our last video is next, reviewing radicals. Reviewing radicals. All right. Ready to go? Any questions? Let's go.
Hi, everyone. Section 0.5 is on exponents and radicals. And we're going to start by reviewing radicals. All right, so if you see this, you should read this as the principal square root of 9. And if you were asked to evaluate this, how would you simplify this? What is this? It is 3, positive 3. And why is it positive 3? Because 3 has the property that when you square it, you get 9. 3 is the principal square root of 9 because when you square 3, you get 9. But now wait a minute. There's another number with the property that if you square it, you get 9. What other number? If you square negative 3, you also get 9. So you could say that both 3 and negative 3 are square roots of 9. In fact, I'll say that right here. Both both 3 and negative 3 are square roots of 9, but our favorite one, Ivanka, as opposed to Eric, our favorite square root is the principal square root, which is the positive 3, the non-negative root. So when you see this radical sign, we're looking for our favorite root, which is preferably non-negative. So the principal square root of 9 is 3, the non-negative square root, as opposed to the negative 3. All right. That's in my notes in this comment here, right? The principal square root of 9 is 3, right? We also say that the principal square root of 9 can be written as 9 to the 1/2. Either way, it's 3, because 3 squared is 9, so 3 is a square root of 9. But because 3 is non-negative, it's our favorite square root. 9 has 2 square roots, 3 and negative 3, but we take the non-negative square root, positive 3, as our principal square root. It's our favorite square root. By the way, why can we write the square root of 9 as 9 to the 1/2? That bears some explaining. All right, so if you take the square root of, I'll go red again. If you take the square root of 9 and you square it, if you take the square of the square root of a non-negative real number, you get that number back. The square of the square root of 9 is 9. Well, likewise, if you take 9 to the 1/2 and square that, now we're going to review rules of exponents later on, very soon, but you might remember that when you raise a power to a power or exponent, you multiply the exponents. You keep the base, 9, 1/2 times 2 is 1, 9 to the first is 9. So it does make sense that the principal square root of 9 can be written as 9 to the 1/2. By the way, if you have the square root of negative 1, that's not real. That's not real. It's I. Later on, we're going to call it I, okay, in chapter 2. But for right now, this is not real. Negative 1 has no real square roots. I'll write that. Negative 1 has no real square roots. Negative 1 is not real. Negative 1 has no real square roots. Okay. By the way, I might abbreviate square roots, like if I'm chatting with people, SQRT. So in a chat, I might use SQRT as an abbreviation for square root. Okay, going back to the notes here. So this here is called a radical symbol. And this in general is a radical expression. Now, the n here is the index, that in green. N is the index. X, which is the insides of that radical. X is the radicand. That's what you're taking the root of. So this is the nth root of x. It's the nth principal root of x. N is the index, x is the radicand. The radicand, sorry, it's the radicand. Now, if you have a square root, then n equals 2, and it's implied. So if the index is 2, we don't have to put the 2 there. We just write the square root of x. We don't have to put the little 2 there. That's assumed. That's implied. Again, the square root of x is also written as x to the 1/2. If x is non-negative, we're assuming that x is non-negative. If x is negative, we're dead. This expression will not be real. We're dead for now. For example, the square root of negative 1 is I. That's not real. Okay. The square root of 0 is 0. For some reason, people forget that. The square root of 0 is 0. 0 squared is 0. All right. Now, again, the nth root of x, also written as x to the 1 over n, right? So, for example, fourth root of 16 can be written as 16 to the 1/4. Okay? It's the principal nth root of x. Here, we have the principal fourth root of 16. Now again, if the index, here it's 4, if the index is even, then the radicand better be non-negative in value, otherwise you're in trouble. If the index is odd, then we have more liberality. Then it's okay for this to be negative. All right. So why is the principal fourth root of 16, or 16 to the 1/4, why is that equal to 2? Well, because 2 to the 4th is 16, and 2 is non-negative. It's our favorite fourth root. See, later on in chapter 6, we're going to see that 16 has 4 complex fourth roots. I'm going to write that out. 16 has 4 complex fourth roots. But only 2 of them are real. Positive 2 and the negative 2. 16 has only 2 real fourth roots, 2 and negative 2. And our favorite one is, of course, the non-negative. 2 is the principal fourth root of 16. It's our favorite root. It's real and it's non-negative also. The negative 2 is our second favorite because it's at least real. But wait a minute. What if we have an odd root and a negative number in here? The cube root of -8 is -2. That does work out. Okay, if you don't see that, let's do another example. Okay, let's see here. What is the cube root of -1? The cube root of -1. Well, the cube of what real number is -1? There's only one real number whose cube is -1. His name is -1. So the principal cube root of -1 is -1. -1 has 3 complex cube roots, but only one of them is real, the -1. And it's the best we can do, right? Because positive 1 won't work. So what's our favorite cube root for -1? Well, it's the real one. -1 is the only real root for -1. -1 is the only real third root of -1. So it is the principal third or cube root of -1. Because no positive number has the property that the cube is -1, the best we can do is this negative number, which at the very least is a real number. -1 is the principal cube root of -1. So the principal root can be negative if you're taking the odd root of a negative number. Likewise, the cube root of -8 is -2. Okay? This is also written as -8 all to the 1/3. You need the parentheses here. We get -2 because the cube of -2 is -8, all right? And -2, although it's negative, is at least a real number. So we can say the principal cube root of -8 is -2. A principal odd root of a negative real number is negative. -8 has 3 complex cube roots, but only one of them is real. Unfortunately, it's negative, but it's the best we can do. All right. X to the m over n can be rewritten in 2 ways. I'm assuming, by the way, that this is reduced. For example, they're not both even, which can be confusing. My footnotes have technical notes, and it gets very confusing if these are both even. This is an easier case where both are odd. You can rewrite this in 2 different ways, 2 different easy ways. You can take the nth root of x to the m. So you basically take the power first, and then take the root. Or you can take the root first, take the nth root of x, and then raise it to the mth power. Okay. I'm assuming that m and n are positive integers, and they're not both even, because that's kind of a weird case. My footnote discusses that. Don't worry about the footnotes. They're very technical details. So x to the 3/5 can be written in two easy ways. You can take x, cube it, and then take the 5th root, or you can take the 5th root of x first, and then cube the result. Which is easier? Well, it depends. All right. So that was a review of radicals. Later on, we're going to discuss laws of exponents and radicals. These are closely connected.
I'm willing to call it a day because normally in an on-campus class, I would stop here and remind me if I forget. If you're keeping up with the lectures after today, you can go up through the homework for section 0.5, number 1. So you can go from 0.1 through 0.4, complete those. And after this, you can do 0.5, number 1. Bear in mind, if this is all review for you, if you already have a firm grounding in this, you're welcome to work ahead. I'm not teaching you different math from what you've learned before. I might do things a bit different here and there, but you're welcome to work ahead, all right? But if you're keeping up strictly with the lectures, then you can go up through homework section 0.5, problem number 1, which has like A, B, C, and so forth. Bear in mind, I'm not going to collect homework until September, all right? But keep up, don't procrastinate. And you're gonna email me basically like a packet of homework sometime in September, that one Friday in September. All right. And again, please remember, please remind me if I forgot to mention that. Okay. All right. So I'm good there. I'm willing to stick around for questions. Okay. People are free to go, of course. I'm not taking attendance anyway, but let me see here. If we work ahead, will you answer questions from sections we haven't covered yet in the homework sessions? Good question. Certainly privately, that's fine. If the whole class is still around, I might hesitate a bit. You can always ask, but you might want to do more of a private chat with me or email or office hours. Is there another Zoom meeting this week on Thursday? Yes. So our class meets by Zoom Tuesday, Thursday, 7:05 to 9:30 p.m. Okay. And I do expect to meet with class, although I don't take attendance, as you've seen. And the homework sessions, whether they're recorded or not, that'll depend on the students. Okay, any other questions? I'm glad that we're ending a little bit early so I can take questions. What's the difference between homework and homework sessions? There's not really a difference. It's just that in boldface, the things I call homework sessions in boldface, do I have my, yeah. This is where I used to have exams. So it just seemed kind of natural for me to take up the exam time with larger session times. Okay, so for example, on September 1st, I might have about 20 to 30 minutes to discuss the homework, whereas on September 3rd, I expect to have an hour and 15 minutes because that's how much time I allot for the first exam. All right, but in either case, I take homework questions. And again, it's a matter of deadlines. So Thursday, September 3rd is our first major homework session, not including this little one over here. And your first homework assignment is presumably due midnight, the end of Friday, September 4th. Unless something drastic happens up here. Yeah, the turn-in dates, yeah. So you'd look more towards the day after the bold-faced homework sessions for the due dates. Again, this is all tentative, as is always the case, but I expect this will stick. Unless there's a huge blackout or something. I don't know. Which has happened, by the way. I mean, I have lost days before due to blackouts. Any questions? Don't get any ideas and run into a lamppost or anything. All right. Any questions? Just, yeah, goodbye. You're free to go, but I'll stick around. I'm always happy to talk with students or chat with students after class. Anything's possible. That's true. Anything's possible in 2020. President Carrot Top. Oh, I could not do that to myself. Okay, and thank you all. Thank you all for sticking it out, and I hope we have some fun. I look forward to working with you all. Thank you.
Thank you, sir.
I'll stick around. I'm happy to take questions either by chat or by voice. And remember, you can also share screen. Thank you all. I'll stick around, but I don't know. Some of these people might be out walking the dog by now, so maybe I shouldn't wait for one, huh? But I see 11 now. Always happy to talk with you. Try not to walk your dog right now if you want to talk with me, but
Hey, I do have a question. For the
Yep.
office hours,
Mhm.
when we're scheduling with those, do you normally expect us to maybe like the day before or a couple days in advance schedule those with you, or is it more just kind of uh, in the hours in and around the
Well,
office
yeah.
hour?
Basically, it's a matter of when I could get to it. I mean, the ideal situation is if you give me advance notice. But if something comes up last minute, it's a question of how often I can access my email and kind of what's going on that day. So, um, if you email me and I can catch your email, certainly when office hours start, I feel obligated to check my email when office hours start. And then, in theory, if a student wants to Zoom meet with me, then it becomes a matter of, well, do students want to meet with me in private? Uh,
Mhm.
but yeah, I mean, yeah, I don't expect a whole lot of people meeting me at once, but sometimes two or three people might see me. Usually on campus, I'd work with a whole group of students. So it's a matter
Mhm.
of maybe who's first, and then asking, so would you rather meet with me privately, or sometimes they like it when other students come in, but students don't mind waiting and allowing people courtesy, first come first serve. It works out so far. I haven't had a problem. So basically, contact me when you can, and if you give me the more notice, I'm more likely to set it up at a good time for you. But I will check my email. I do expect to check my email during office hours, unless I'm really rushed on videos. So there might be days when I
Mhm.
feel really rushed on videos, but we just try our best. So try me anyway. Either advance notice or try me during office hours. You can email me, and I should be checking my email throughout my office hours anyway.
Mhm.
So just try me.
Okay. Thanks.
Sure.
All right. Have a good one.
You're welcome. Would you mind explaining again about the homework session? Is that a test? Well, the homework, you're going to be graded on the homework, okay, which you're allowed to take home, work with people on, but just don't copy mindlessly. Make sure that you understand what you're turning in, right? Um, oh, yeah, I understand bad connections. No, I dropped two. Um, so are you talking about the grading of the homework? So yeah, the homework kind of takes the place of a test in terms of the grade. Yeah.
Hello, Professor. Hello.
Hello, yes?
Hi. Yes. So, regarding homework, so I can find it on your website, right? It's gonna be the one that's due. The first homework is gonna be chapter 0, right?
Right, chapter 0, and that's due. I guess it's going to be due September 4th, Friday, midnight, end of the day, September 4th. So the day after the major homework session. The idea is that I want to give students plenty of time, opportunity to ask me questions, whether it's in class or in office hours.
Okay, sounds good. And yeah, I guess that's it. Okay, thank you.
You're welcome. Okay. All right. Anything else? Anything else? It's like a video game where it's 6. Always willing to talk with you, but if you have to walk the dog, you got to walk the dog. Yeah. But log off first if you walk the dog. All right. Good night. Good night, y'all. right. Any last minute questions? Questions? All right. Any questions? Any questions? I'll wait one more minute to see. Okay, is that everyone? All right. Okay, take care, y'all. All right.